Okay, so I'm going to introduce intermolecular forces here. I do so because we can based on a molecule's polar or polarity, predict what kind of intermolecular forces are present in a molecule. So since we've just finished our discussion of polar molecules in Chapter 10, along with molecular geometry, we're going to introduce this here, but we'll talk more about it when we start Chapter 11 and look at the physical properties of liquids. So we're going to start by defining what intermolecular forces are, and these are the forces that attract molecules together. Okay, so attractive forces between molecules versus intramolecular forces, which are the forces that hold molecules together, or in other words, the chemical bonds in a molecule. So intra is chemical bonds, inter are forces outside the molecule. Generally, intermolecular forces are weaker than intramolecular forces. And we can also relate intermolecular forces, and I'm going to start calling them IMFs, by boiling points. So we can compare boiling points between different types of molecules and relate them to the type of intermolecular force present. So this also can be related to melting points, heat of vaporization, heat of fusion, heat of sublimation. So dispersion forces. So these are stronger than, I'm sorry, dispersion, we're still on. I thought we were jumping ahead to dipole forces. Never mind. Polarizability. So this is a measure essentially of how easily the electron distribution can be distorted in an atom or a molecule. And basically that depends upon size. For one, it increases with an increasing number of electrons. So as we're adding electrons, we're also adding protons and neutrons, obviously. So the atom or molecule, depending upon what we're talking about, is getting bigger. And as we add energy levels to a molecule or to an atom, we know that the distance from the nucleus increases, the subshells get larger, and therefore we have more diffuse electron clouds. So dispersion forces are going to increase with increasing molar mass. And that trend is observed here in this table from your text, where the first compound here is methane. It has a melting point of minus 182.5. And as we change the terminal atoms that are bonded to these carbons, they are increasing in size. And we see that increase then, oh, I didn't mean to draw this type. We see an increase in melting points as those molecules get bigger and those dispersion forces get stronger. Dipole-dipole forces. So these are stronger than the dispersion forces, and these forces occur in polar molecules. So remember, all molecules have dispersion forces, but dipole-dipole forces are only in polar molecules. So in order to assign IMFs to a particular molecule, we need to be able to predict its polarity. This diagram just shows you the orientation of polar molecules as they would arrange themselves in a solid. So they're going to orient themselves to maximize those plus minus attractions. This also occurs in liquid samples, but they aren't as ordered as they would be in a solid. Oops. And the last and the strongest of the IMFs is something called a hydrogen bond. Now, this is not a chemical bond. It is an electrostatic attraction. So it's a special type of dipole interaction, and it involves only hydrogens that are bonded to an N, O, or H, and the bond, the hydrogen bond or interaction occurs between a hydrogen and an F, O, or N. Okay, so there are criteria that must be met here. So it's very special, and not many molecules hydrogen bond. But the best example of a molecule that can hydrogen bond, of course, is a water molecule. It has two lone pairs on that oxygen atom, and we have a hydrogen bonded to it. And in another molecule, the hydrogen, remember this end is partially positive, this hydrogen will be attracted to the partially negative end here and form the hydrogen bond, or that interaction, with that lone pair of electrons. This also happens in ammonia. So remember, F, O, or N's with hydrogens can hydrogen bond with other F, O, or N's. So one of the hydrogens, remember, lone pair, we're going to have that dipole moment going in this direction. So this is partially positive. This electron partially, or these lone pairs set up that dipole, so we can have that hydrogen interact with the lone pair on nitrogen. And the last example, well, they don't show it by himself, sorry. HF. This shows HF interacting with ammonia, but HF, we've got a hydrogen bonded to a fluorine, and a hydrogen bonded to an N, another F, or an O, can also hydrogen bond with a lone pair of electrons on that fluorine atom. So I'm going to introduce a couple of properties of liquids here. We'll talk about them more in chapter 11, but they are related to the intermolecular forces between molecules. So I'm going to mention them here, but we'll talk about them more also when you do your lab exercise for IMFs, or your lab activity. More discussion and examples will be given, some demos in fact. But surface tension is the amount of energy required to stretch or increase the surface of a liquid by a unit area. And if you look at this beaker, it has water molecules in it, and we can envision this water molecule. It has water molecules surrounding it completely. So it's really rather stationary here in the center. This water molecule, however, is being pulled from side to side and then down. And that's what helps keep it at the surface. But depending upon how much kinetic energy it has at a time, or in a point in time, it can escape from that surface. That would be involved with that evaporation, which we'll also talk about. But surface tension then can also kind of be um, thought of as elasticity. How elastic is the surface? How far can it be stretched? If we have strong IMFs, we have high surface tension, okay? And water has a very high surface tension. As I said, you'll see some demos in the lab activity, but if you think about maybe walking in a park or around a pond and you've seen water bugs appear to walk around on the surface of the water, they are not breaking that tension. It can be broken, of course, but the surface tension of that water is holding them up. Two other properties of liquids are cohesion and adhesion. There's also a demo in the lab activity of this at work, kind of. Well, it is, but on a larger scale than what I'm going to describe here. Cohesion is the intermolecular attraction between like molecules, and adhesion is an attraction between unlike molecules. All of you, or most of you, likely have had your finger pricked at the doctor's office and had a capillary tube with an open end touched to that bead of blood that's on your finger. And what happens? It wicks up that capillary tube, which is made of glass. So these are the two forces that are responsible for what's called capillary action. So when this process is occurring, we have like molecules, the blood molecules, being attracted to one another, but we also have an attraction between the blood and the glass in the capillary tube. I think that wraps up that discussion, but I want to do, oh, no, not quite. One more, viscosity. So this is a measure of a fluid's or liquid's resistance to flow. There are some demos of this, and you're also going to be watching some races between liquids in your lab activity. But here's a table from your text that gives viscosity in Newton seconds per meter squared. Those are the SI units for viscosity. And if we look at acetone, what do we know about acetone? I think from experience, you know that it evaporates easily, correct? So, even though we haven't gotten there yet, that means that it's easy for acetone molecules to escape from the surface of a liquid. And thus, we see this low viscosity measure because it has weak IMFs. So its ability to flow is quite easy. Right? So it doesn't resist flowing, it flows quite easily. So that's a 10 to negative 4 factor. Compared to water, we have 10 to the negative 3. So it flows a little less than, well, a factor of 10, magnitude of 10 less than acetone. But look at this molecule. Its viscosity is 1.49. Water, as we know, Lewis structure. Glycerol is a 3-carbon molecule, and it has 3 hydroxyl groups attached to it. And actually, I should have drawn that like this, perhaps. Has 3 of these. What can happen? Can glycerol hydrogen bond? Yes, it can. And it has more ability to hydrogen bond than a water molecule. And if anyone knows what glycerol looks like when you try to pour it, it is very thick or viscous. So it has a high resistance to flow or a high viscosity. So stronger IMFs, even though both glycerol and hydrogen bonding have the same kind of IMF, the glycerol molecule can make more hydrogen bonds than water molecules. So stronger IMFs, higher viscosity. All right, so now what I want to do is just give you a couple examples of the types of questions you might be asked on your third exam with respect to this discussion of intermolecular forces. And as I said, we're going to relate the IMFs to polarity of molecules, excuse me. So I have H2S, and I want to know, or I want to predict, what types of IMFs this molecule has. So the easiest way to do that is to actually draw the Lewis structure, and I'm not going to go through the steps of drawing Lewis structures in this discussion, but this molecular geometry is bent. Electron geometry would be tetrahedral, and we've got lone pairs on the central atom, so this then is a polar molecule. And if we were to list the IMFs present, we know that all molecules have dispersion forces, but this is also polar, so it also has dipole interactions, 2 different types. CCl4, carbon tetrachloride. I'm not going to put all the electrons on the chlorides or the chlorine atoms, but they have a full octet. Is this polar or nonpolar? We have polar bonds, but we have symmetry, so we have a nonpolar molecule. So what types of dispersion, or what types of IMFs are present? I said it, only dispersion forces, or London dispersion. How about this one? Sorry, a little stuffy this morning. This is a chlorine atom. So this was nonpolar, but now I've changed something. I've got 3 hydrogens and a chlorine atom here. So now I have a polar molecule. And if I have a polar molecule, we definitely have dispersion, or London dispersion forces, because all molecules have those. And we have dipole-dipole. What about, I'm going to switch to the next page. This molecule. We've discussed the fact that this is an organic compound, and the class of compounds is an alcohol, characterized by that OH group or hydroxyl group, which again is not the hydroxide ion. Okay. And if I draw the Lewis structure of this, I find, well, the central atom, well, this would be polar too, but we do have a dipole moment here, permanent dipole moment. So we have a polar molecule. And remember, I told you, I believe, that as this carbon chain grows, this has less effect on the polarity of the molecule. It would be nonpolar. If we get a chain of carbons probably grade 6 or greater, but these small alcohols are polar, and this again is methanol, so methanol, ethanol, propanol. Polar, so we have dispersion forces, or London dispersion forces, or London forces. We have dipole-dipole. Do we have anything else? And the answer is yes. We have hydrogen bonded to oxygen. So this can form hydrogen. Oh, made a mess of that. Whoops.